Hey everyone, today I asked ChatGPT 5.2, Claude Opus 4.6 extended, and Claude Sonnet 4.6 extended. Similar question, that is, what mathematical formulas or frameworks are not commonly used in current LLMs but could potentially be used to train or build language models? So here means I am saying that what are the formulas that is commonly not being used in LLMs but can be used. Okay, so this is a deep research level question and it aligned very well with this. I will go beyond surface sensor and focus on mathematical frameworks that are okay. So here that is category theory, and then we have information geometry, very underused, and then we have almost untapped, this one category theory. Then we have topological data analysis, almost never used. Then we have graph theory beyond attention, lightly used. Then we have dynamical systems and differential equations. uh, Language is stateful and contextual. And then we have symbolic logic plus proof theory, mostly external. We have compression theory, rarely used explicitly. And we have energy based models and statistical physics. This is what it is giving. We have causal inference, barely integrated. Algebraic structures, heavily ignored. So we have, this is in big picture summary. This is framework, this is used today, and this is potential impact. So category theory, almost never used, and this is potential impact, structural reasoning. Then we have information geometry, very rare use. We have topology, never used, it is saying. We have graph theory, advanced, partial used. Dynamical systems, rare use. Symbolic logic, external. Then we have compression theory, rare used. Energy models, limited used. We have causality, barely. And we have algebraic structures, ignored. Then I asked, tell me how it can make LLM training better. So what it is saying, why LLM training is inefficient today. That is interesting, right? One LLM is saying that why LLM training is inefficient today. Okay, so this is baseline. So current LLM training problems: brute force skill, learn everything from gradients over tokens; redundant learning, same concepts relearned across layers and epochs; um, slow convergence, no notion of structure; catastrophic forgetting; hallucinations. So these are things. We have information theory, faster, more stable training; problem in current training, gradient descent assumes parameter space is flat, but probability distributions live on curved manifolds, and it is saying how this improves training. Then this is training benefits, effect. Then we have graph theory, stop relearning the same knowledge. Current issues is transformers store knowledge diffusely. Every retraining equal to re-encode concepts. graph based learning, instead of weights equal to memory, use nodes equal to concepts, edges equal to relations. Training becomes add nodes, strengthen edges, reuse existing structures. Fantastic. Then we have category theory, learn structure once, reuse forever. And we have dynamical systems, training reasoning, not token. Then we have compression theory, better generalization with less data. And we have topology, knowing what the model does not know. Interesting. LLMs always insert even when wrong. Topological training, track holes in representation space, unconnected regions, boundary crossings. Then energy based models, consistency without overtraining. Casual inference, robust learning under distribution shift. Symbolic type systems, training with guarantees. What training looks like after this shift. Today, data, token, transformer, loss, repeat. And then he has with math heavy frameworks, structure, concepts, graphs, dynamics, minimal updates. Then we have key insights, more important. Now we'll see what Claude Opus 4.6 is saying. So this is fascinating question that sits at the intersection of mathematics, theoretical computer science, and AI research. Here are several areas that are underexplored relative to their potential. Then we this is tropical geometry and tropical algebra, safe theory, safe neural networks, category theory, beyond attention, persistent homology and topological data analysis, then non-commutative probability and free probability theory, homotopy type theory, then information geometry beyond Fisher. Lot of things are there. Then we have tell me how it can make LM training better. Then great question, let me connect each framework to specific concrete problems in current LLM training and explain the potential improvements. Then we have lost landscape navigation, tropical geometry. Then practically this could enable smarter learning rate schedules that detect when you are crossing a ridge between linear regions. Isolation strategies that start in favorable polytropes. Then we have uh, then information geometry beyond Fisher. The reason why training large models require extensive hyperparameter tuning, warm up schedules, and sometimes just fails catastrophically. Fixing hallucination coherence, safe theory. Hallucination happens because the model generally locally okay safe over attention graph. Okay. Then we have homotopy type theory. Assess token sequences to train the model to be invariant within them. Interesting. Then we have better representations in embeddings, persistent homology, training dynamically, uh, training dynamics and stability, free probability theory, ergodic theory, alignment and transfer, scaling argument. Now we'll see what Claude Sonnet 4.6 extended is saying. So great question. There is a rich space of mathematical ideas that are underexplored in the context of LLMs. Here are some of the most promising ones. Differential geometry and Riemannian manifolds, algebraic topology, persistent homology (TDA), category theory, optical transport, geometric algebra, Then we have these things, common threads. Then this is the one, tell me how it can make LLM training better. Then tell me, let me go through the most concrete ways each framework could improve training focused on real problems LLMs currently have. Core problems LLM training today is are poor sample efficiency, unstable optimization, lack of systematic generalization, poor calibration, uncertainty, representation and representational limitations. Each framework addresses one or more of these. Okay, here parameters. Here it is showing a better representations with fewer parameters. Then we have information geometry, better optimizers. We have optimal transport, better loss functions, topological data analysis, regularization and representation health. These are the things: geometric, algebra, category, theory, the ununified feature. This is fantastic. Thanks for watching. Stay connected to your Superflow.